Hi, I'm Old Dog Charles, and welcome to this Fundamental Aspects of Electrical Engineering. This is part 5, where I'm going to talk about some circuit fundamentals. Now, it's traditional to include an introduction, so here's an introduction. This is all the crap I'm going to talk about. Here's the thing.
Hello. In order for electricity to work, there must be a conductive path between the positive and negative of the supply, in this case, the batteries. When there is no path, there is no current. When the switch is closed, the path is completed and the current flows, lighting the lamp. So there.
We usually compare electricity with the flow of water because in some senses they behave very similarly. Here's the thing.
Hello. The behavior of water can be compared with the behavior of electricity. Here there is a pump, a turbine, some pipes, and some gauges. The pump is like a battery that converts chemical energy to electrical energy, or whatever thing you have that converts one form of energy to electrical energy. When switched on, the motor converts electrical energy into mechanical energy that drives the pump, which uses the mechanical energy to create pressure energy, which is like voltage in electrical circuits. The fluid is contained in the pipes, which is like the wires in a circuit. Like wires, the pipes have a resistance, in this case, friction, and there is a slight pressure drop along the pipes. The fluid flows through the pipes, the same that electrical current flows through wires. The turbine provides the load. It uses the energy in the fluid and converts that into another form in order to do some work, and there is a large pressure drop across the turbine. The fluid finally flows through the pipes, and back to the inlet side of the pump, thus completing the circuit. So there.
There's only two ways to connect an electrical circuit, either in series or in parallel. I'm going to jabber on about each of these. Series circuits are connected input end to output end, kind of one after another, much like you picture a load of elephants walking, each one's trunk grabbing the tail of the one in front of it. And you always have to make sure there's a return path. This isn't how elephants work, though. The voltage is divided between loads as a function of their individual resistances. And because there's only one path, the current's going to be the same through all the component parts of the circuit. The total resistance is going to be the sum of the individual resistances. So here we have a circuit. And what we've got is some batteries here. There's a voltmeter across the batteries, which gives the battery voltage, and the current flows around the circuit. First it flows through the ammeter, which shows how many amps are flowing. Then there's the load, which in this case is a bulb, that all the voltage is dropped across the load because there's only one lamp. And then there's the return path. If we add another lamp in series, we notice firstly that the bulbs get a bit dimmer because the total voltage is actually shared across each bulb. In this case, the total voltage is equal to the voltage across the first bulb plus the voltage across the second bulb. The current also is lower because the total resistance is higher. Of course, the total resistance is the resistance of the first bulb plus the resistance of the second bulb. If we add a third bulb, the bulbs get even dimmer. The total current also decreases again in accordance with Ohm's law because the total resistance has increased. We don't use series circuits very much because most things are connected in parallel. Occasionally we use things in series, for example, sometimes in traction motors, and I'll talk more about traction systems in a future video where I'll explain more. Parallel circuits, the loads are all connected to the same 2 points of the source. So the voltage across each load is going to be the same. And the current is basically going to be the sum of the currents through each load. the total resistance is going to be lower than the lowest individual resistance. This is because the total resistance in a parallel circuit is the reciprocal of the sum of the reciprocal values of the individual resistance. Yeah, that sounds quite complicated, but it will come clear if I use some pictures. So here again, we've got our basic circuit. We've got the battery voltage, the current, the bulb, the resistance. If we connect another bulb in parallel, what happens is the initial bulb doesn't change. It still has its resistance and it still draws the same amount of current. The additional bulb is as bright as it wants to be because it's also getting the full voltage, and the current through this bulb is whatever Ohm's law says it's going to be. The total current is going to be the current through the first bulb plus the current through the second bulb, and the total resistance is going to be the reciprocal of the sum of the two resistances. Now, if we add a third bulb, you can see that the total current goes up even further because now we have a third bulb that's going to draw its own current in accordance with its resistance and the voltage from the batteries. Then what you get is a circuit that has even more current, and if we keep adding bulbs, it will keep increasing the current, and eventually the fuse will blow. Most things are connected in parallel, your house, electric trains, and all kinds of shit like that there. To recap, this is all the crap I've talked about in this short video. That just about wraps it up for this part. Thanks for watching. Now we understand the different ways that components can be connected. I'll be back in the next part, which is about passive components. I think that need be all.